And what we're talking about today and tomorrow is the three-dimensional versions of them, the generalizations. So if you recall, we had, when we started the chapter, we talked about the circulation curl theorem in section, well, the book really takes it up in section 16.4, but as we did things, we were talking before that. So Stokes called the integral around a closed curve that's you take in the counterclockwise direction if you're thinking of the curve in the xy plane and thinking of k as the normal to it. A circulation integral. So this is the line integral of the tangential component. You could also have written this f dot dr. And although the book doesn't say it this way in section 16.4, it's equal to the curl of the field, dotted with the normal to the area that the curve encloses, which typically is k if you're thinking of these as curves in the xy plane, which is how Green thought of it and how the book thinks of it in section 16.4. So what is required is that the closed curve is the oriented boundary. So I'll be talking today about just what this oriented means, and that relates to your little models there of what we call a simply connected domain. In the plane, simply connected means that there aren't any holes in it. If you read the book about simply connected, their example is that if you think of a closed curve, you have to be able to shrink it down to a point without ever getting out of the domain. So if you had in the plane, if you had a hole bored through the paper, then you could have a closed curve that would surround the hole, which would be points in the domain, but you couldn't shrink it down without falling into the hole and getting out of the domain. If you get something with holes like that, then these theorems are not necessarily true anymore. If you're thinking in 3 dimensions, something like a block of Swiss cheese that has various holes in it could still be simply connected, because you could shrink the curve down to a point, and because of the way the hole is in the brick of Swiss cheese, you could slip past the end of the hole, so you could stay in the domain. So no holes fits if it's a plane region, but as the requirement. But if you're in 3 dimensions, it's not that simple, because you could have some holes like the air holes in the cheese and still be able to shrink the curve down. But what you can't have is a hole drilled clear through it. Okay. So then we also have the flux divergence theorem, the other what books often call the normal form of Green's theorem, if you're still thinking in the sense of section 16.4, where you're saying that the circulation of the outward flux, the F dot n, is equal to the divergence of the field integrated over, in the case of 16.4, it would be over the area that's enclosed by the curve, the region. So if your field is has components m and n, and your outward normal ds has the form dy minus dx, then this dot product is m dy minus m dx. And the corresponding divergence of this is the sum of partial derivatives. And the scalar form of this then, as it appears in 16.4, looks like this. So the point I'm making is that if you think of these two theorems in the vector form, this one and this one, then you can see how to do the three-dimensional generalizations. So Stokes' theorem, which again is the generalized circulation curl, is this repeated, except now you're talking about the surface sigma and the outward normal for the surface. So you have to be able to get the outward pointing normal in some consistent way that's related to how you would do this circulation integral around the boundary. So this is one of my high-priced models. Say this is a Stokes theorem surface. You see, it's an open surface in the sense that if you do this, the pan spills the water. So it has a boundary. That's the rim of the pan. And the orientation, the relationship between the outward pointing normal and the circulation goes with your right hand with thumb and fingers. So the thumb points like your normal, and as you move this toward the boundary of your curve, remember that's the rim of the pan, the way your fingers for your right hand want to point is, if you're looking down like this, the counterclockwise orientation. So you have to be able to get this normal in a consistent way from your formula that would be the outward pointing normal consistent with counterclockwise circulation around the boundary. So that's the reason for these little things, because you see the way that you make this, you take your sheet of paper and you rule a line. So when the paper's flat on the table and you draw the line, it's clearly on one side of the paper. Okay, you cut the strip and you make the twist in it and you staple it together. Well, you see I have the little letter F and I have the little letter S, if you notice. So you think of this curve, you start and where you see S, and you think of things like thumbtacks that you imagine that would be the normal going through your curve. So if your S is, as I'm holding it, on the kind of the, what you might call the inside pointing up, you go around, and by the time you get to the finish, you see your thumbtacks that are pointing the normal are pointing the other way. So what you have, you see, is a one-sided sort of surface. So you, that's the sort of thing where your Stokes theorem isn't true, because you don't have a consistent way to relate what you would call an outward pointing normal to the way that you're going around a curve. In other words, which way is outward? Well, you start out, say, you think this is, but you just follow the curve, and where you end up is just opposite to it, whichever way you want to go with it. So not everything is orientable. There's also a more complicated thing that's called a Klein bottle, Klein, which is another example of something that's a one-sided surface. Felix Klein was the department chair in mathematics at one of the universities in Germany in 1870s, 1880s, along in there, and he came up with what's known as the Klein bottle. So anyway, for everything in the book, of course, the Stokes theorem is going to work. You have to kind of do laboratory curiosity to get something where it doesn't. So what I've just been saying is what I've written here. So the other so we have the Stokes theorem is the generalization of the circulation curl Green's theorem, and that's section 16.7 that is where we focus our attention today. And then the divergence theorem, as it's called, is the generalization of the flux divergence form of the Green's theorem. In other words, what's often called the normal form. So Gauss introduced the divergence theorem, according to the story, in the class that he was teaching. He taught at the university in Göttingen in Germany. And that's one of those GOE with the two dots over the O, Goettingen, and it's something like Göttingen. And he had a student from Russia named Ostrogradsky, and Ostrogradsky took down the class notes, and Gauss had presented this in class, but he hadn't actually sent it off to a math society type journal. And so Ostrogradsky published the thing, and so the Russians call the thing Ostrogradsky's theorem, but all he did was send in the class notes. We call it the divergence theorem, or else Gauss's theorem. So anyway, we'll talk about that tomorrow, but what that says, as you can see if you look at it like this, is that you can compute flux integrals if it has to be a closed volume. So it isn't the same kind of thing as Stokes' theorem. Stokes' theorem, remember, is an open surface in that in some orientation it would spill water. The divergence theorem that comes tomorrow is a closed surface, so like a closed sphere or something, or a box with all 6 sides, something that would hold water. And so it says that if you do the flux integral over the surface, and of course it has to be an orientable type surface, that'll equal the triple integral throughout the volume that the surface encloses of the divergence of the field. And so often the easy way to do things is to do the triple integral of the divergence. You know, divergence is scalar, so it's a triple integral like in chapter 15. And we'll do those, that's section 16.8 we'll do tomorrow.
So a donut wouldn't work because there's a hole in the middle, right? Is that right?
Yeah.
Okay.
Well, it would, let's see, I was trying to think about that for a second. It depends on how you define your domain
Okay.
with that. You could do the flux integral over the surface of the donut, and then what it would be what it would have to equal is your volume throughout the interior of the donut.
Okay.
So anyway, back to 16.7. Problems 1 through 6 want us to compute the circulation around the boundary by computing the flux integral across the Stokes theorem type surface that that we call sigma. So, for instance, if you look at problem 3, sigma is the portion of the plane, this plane, which intersects the x-axis, y-axis, and z-axis at 1. So you see my 3 intercepts. And then this is x, y, and z as always. And so when z is 0, and you're down here in the xy plane, this edge is x plus y equal 1. So what you have to do, if you're going to do the flux integral over this slanting surface that I've tried to indicate with my blue colors, you have to get the outward pointing normal, like that. See, that is the way you'd want it to point. You want to picture taking your right hand. You have this slanting plane, and you put your right hand on it, and as you go toward the edge, you see how the fingers point. So you'd be coming up that edge. So that would be like that. And then you'd be going down that edge, and then you'd be going across like that. So, see if you be going that way and that way across and up that way. So I probably should have put the arrows on it. So you're chasing it around like that. So to get the normal, then, if you have the equation of a plane, remember you go back to chapter 12. If you have the equation of a plane, something x, something y, something z equals a constant, then the coefficients 1 in this case are what we call the attitude numbers, chapter 12. Remember, we use the word attitude the way you would if you're thinking of flying and atomic submarine or anything that has 3 degrees of freedom. So your normal is 1, 1, 1, and then your unit normal, which is what we need here for the flux integral, is 1, 1, 1 over square root 3. So if this is your field, this is what the problem gives, you do the curl, and you get this, then you're doing curl f dot n, which is this vector, and so that comes out that way, and then you can collect your terms, and so you have this. Now, you're going to work this as a parameterized integral over this surface, so that means that you use from the equation of your surface here, say, solve for z in terms of x and y, like this. so that then your parameters are x and y. And so then what you're going to do is work the dot product here of your curl with your n, which is this, and then parameterizes when you replace the z like this. And you had the square root of 3 in the denominator to get this to be a unit normal, and then if you're working this as a integral over this surface with the variables down here in the projection area, this triangle R that's green, your projection factor is also square root of 3 because it's the magnitude of the gradient of z minus f of xy. That's from doing surface integrals like we were doing last week. So you both multiply and divide by the square root of 3, which you see I'm doing here and canceling it out. When it is a flux integral, as opposed to just surface integrals, it turns out that this magnitude of your normal and the projection factor are the same thing, and they cancel out. So what you really end up doing is the integral of your curl dotted with the normal as opposed to unit normal over to integrate them as a flux integral. So integrating over this region, if I'm thinking of y going from 0 to the line x plus y equal 1, it's going from 0 to 1 minus x, and then my projection on the x-axis is 0 to 1. And so then you work this out and you get what the book says it is. And this is also what you would get if you did the actual circulation around the boundary of the original field. Notice if you did that, you'd have to do 3 integrals because your boundary would be this one, that one, and that one. So you'd have to set up the 3 line integrals and add them up. They don't ask you to do that, but it ought to come out. Okay, any question on 3 here? So remember that when it's a flux integral, as opposed to just a surface integral, you're going to have f dot the normal times a projection factor divided by the magnitude of the normal, and the magnitude of the normal and the projection factor will cancel, so you just have f dot the normal, really. And then you work that by parameterizing with the equation of your surface. Well, look at 4. So this is your field, and you do its curl, which certainly is not 0 in any, not identically 0 certainly, and the function that and we're working with the same slanting plane. So then if you do the curl, which is here, then you get a normal, not a unit normal, but a normal. So that is the gradient of z minus f of xy. And then to get a unit normal, you'd be dividing by the magnitude And to do the projection factor, you'd be multiplying by the magnitude. So I ought to have the bars on this. Divides out anyway, but that's a little better. So you just have curl and a normal, whichever way you get it. There's more than one way you could get a normal, but if you have a plane like that given as z equals f of x, y, then one way is gradient of z minus f of x, y. That gets you an upward pointing normal. And you see, you want the upward pointing normal to be consistent with the orientation around the boundary, like that. So, then what you end up with here is the curl of your field, the normal to the plane, which is the 1, 1, 1, not the unit normal. The root 3 and root 3 would have canceled. So you dot that out, and that gets you all this. And what I've done is to replace the z there and there with 1 minus x minus y. And if you write all this down and start canceling, you end up with 0. As it turns out, it all cancels out. And so our line integral then would be 0, because the double integral of 0 would be 0. And so you can have problems where a line integral around a closed path is 0, even though the curl of the field isn't 0. So curl f is 0 is sufficient for the circulation integral to be 0, but it isn't necessary. So if your circulation is 0, that doesn't necessarily mean that the curl is. It can be a curl that gives you something so that when you do the dot product to the normal of that curl with whatever is your surface, that dot product will, when you parameterize it, that'll all just cancel out. This is another example of that same sort. This time we're going around the square in the XY plane. And you see here again, if you try it, if you take like a sheet of paper and put it on the table, say your tabletop's the XY plane, put your hand on that, this is up, okay, go that way, so you're going that way, and you're going this way, then I'm coming this way, and I'm going that way. So much for gymnastics, at which I am not any good, obviously. Okay, but you get the idea of how the arrows are going to go relative to this one sticking up. Okay? If people didn't have hands, they'd never have done this stuff. Okay, so the normal's k, and it's a parameter. Here is our field. It isn't, let's see, it isn't quite the same as the one in problem 4. This is different. So you do your curl, and you get this, and then you dot with k, and so all you have really is the k component. So the Green's theorem then, since we're actually in the xy plane, it's the same thing as the so-called normal form of Green's theorem. our circulation then is this K component of the curl integrated over the square. And if you work this out, even though this isn't zero itself, you work this out and you get zero. And so again, you can have the circulation equal to zero even though you have a non-zero curl. Certainly if you have a curl that is zero, your integral with the curl in it is going to be zero, and then you'll have a zero circulation. So it goes one way, but it doesn't go the other way. Well, let's go to the other end. So if we go this way, this is the other type. It's the same Stokes theorem, but you may have your surface given parameterized with the capital letter R symbolism like this. So they want us to get the curl dotted with the outward normal, so the flux integral in the direction of the normal with the parameterizations and the limits as given. So if you look at problem 13, this is your field, you do your curl and you get this, and our surface is a paraboloid. You see, this is z equals 4 minus r squared. So that means that if you did the cross sections, they'd be parabolas opening downward. So you're given this parameterization, which you see if you're thinking of cylindrical coordinates, this is x, this is y, this is the z. And the r and the theta are cylindrical coordinates, but it's set up as a Cartesian vector, x, y, z. So if you do your partials with each of your variables or parameters, you get your partial with r and your partial with theta, and they give you these limits for r and theta in the problem. So for a normal n, not a unit normal, but for a normal, when you have a surface defined parametrically with two parameters, you can take the cross product of the partial derivatives, and that gets you a normal. We talked about that last week. And so I take my partials and I do my cross product. Okay, so then curl f dot n will be curl f, the cross product, and you see this cross product is not a unit normal, but if you divide by the magnitude to make a unit normal and multiply by the projection factor, which is also the magnitude of this cross product, they cancel. That's the same as what was canceling on the other end of the room. So you don't really have to get this magnitude. All that you have to get is this cross product to get the outward pointing direction, and then dot that with the curl. So we're just going to use curl f dot the cross product of the partials with the two parameters u and v, whatever they are, whether they're the cylindrical coordinate parameters like 13 or whether they're the spherical coordinate parameters like problems 17 and 18 that we'll do. So what we have, here's our curl, and our cross product here is this, which I wrote it out as cross product down here to remind you where we got this. And we don't care what its magnitude is, because actually we have this as the result of having found the magnitude and multiplied by the magnitude and having canceled them. But you don't have to do that every time. So then you integrate this as a surface integral. You see, it is scalar. If you multiply out the dot product, you get this. And if you integrate with r, there and there and there, you see my integrations with r and put in the limits, then what you have when you are finished is you have 80 cosine, you have 8/3 sine, and then 4 times 3 over 2 gives you 6. Well, these two integrals are both 0, because the integral of cosine is sine, and sine of 2 pi is 0, and sine of 0 is 0. The integral here is minus cosine, and cosine of 2 pi is 1, and cosine of 0 is 1. So that integral is 0, and that integral is 0. So those are both gone, so you don't have to do them really. So what you have is the integral of 6 from 0 to 2 pi, and that'll get you 12 pi. And that's what they say it is. Okay, so then 17 and 18 are the same sort of thing, except that you're using the two angles from spherical coordinates as your parameters. So you have this field and this for the curl. And your sigma is like the northern hemisphere of an Earth that has radius √3. And so you use the spherical coordinate parameterization for your surface, which is your radius, and then sine phi cosine theta, radius sine phi sine theta. This is x, this is y, this is z. And you do your cross product of your partials, and you get this. And then you do curl from here, dot the cross product of the partials from here. So that's what all this is. And what it leaves you when you work all this out is so you have 0 times this one, and you have 0 times that one, and you have -5 times that one. So 3 5s are 15, and then you have sine phi, cosine phi. Notice both of them are phi's here. And so you integrate with phi, well, that's a u substitution. U is the sine, cosine phi d phi is du. So you have u square over 2, so you have sine square over 2, 0 to 2 pi, or to pi over 2 rather. Sine of pi over 2 is 1, so you have -15 there, and over 2, and then you integrate with theta and you get 2 pi. So you have -15 over 2 times 2 pi. And that's what they say it is. Okay, so if you look at 18, This is another one of these where it actually comes out to be 0 over here, even though your curl isn't. So you have a field here, and your curl is this, which is certainly not identically 0. And our surface is, again, the top half of a sphere. This time the radius is 2. So again, if we do our partial derivatives with the two angles and do the cross product, what you always get for these things that are on a sphere, where your parameters are the two angles, when you do this cross product of the partials, you're always going to get the squared radius. So the 2 square is the 4. Like here, the square of this was the 3. And then you get sine square of the phi, cosine of the theta, sine square phi, sine theta, sine phi, cosine phi. That's always what that cross product will give you for that type of thing. And if you went ahead and ground out the magnitude of this, you don't need to do that to work the problem. But if you did, if you got the magnitude of this cross product of these partials, so you go through these steps, what you will get is your squared radius then, sine of phi, and that's the thing that was the volume of the little box when we were in chapter 15 going to spherical coordinates, where you had rho square sine phi d rho d phi d theta and so on. So the generalization for the surface of a sphere, radius A, is that your projection factor then is the squared radius sine of the phi. However, if you're doing a flux integral, you can go from here on up here. So you have curl times this cross product. So here's your curl, and this is what we got for the cross product. Now you'd parameterize the curl with y as radius sine phi sine theta, z is radius cosine phi. So replace the z and the y, and then do your dot product and simplify that. And first you'll have this integral. It's this term, and this one. So the brackets start here and go there. And then do your integration with phi, and that'll get you this. And now you can see that your flux integral will be 0 if you integrate these with theta, because again, your integral of cosine, 0 to 2 pi, where did I have it, is 0. And your integral of sine is 0, and your integral of sine is 0. So you have 0, 0, 0. So your flux integral comes out to be 0, even though you don't necessarily have to, that doesn't mean necessarily that your curl was. So let's look at some maple here before we give up on this. So I have 2 sets here. This first picture looks kind of like a Christmas ornament, don't you think? You see, again, if you have two or more plot structures, you need the display. So implicit plot, the x squared plus y squared equals 4. And you see that's going to be your cylinder. And then implicit plot, the x squared plus y squared plus z squared equals 16, and that's your sphere. So that's your problem 6. With 13, which we did over there by the door, you see the paraboloid, the figure where a cross section would be a parabolic type curve. And 14 is similar. With 15, you have a cone, and 16, you have a cone the other way. Then 17 is one of these paraboloids again with the cylindrical, well, no, I guess it's actually a hemisphere, isn't it? It's a hemisphere, and I turned, with the mouse, I turned the box off on the side so that you could see there is an inside of it. And then 18 is our hemisphere also. So then, if you look at using vector calculus, so you have to set your coordinates, always have to do that. And then with problem 6, defines the field. And so if you ask, you can get curl, and that's line 3 there, and give it a name. And then if you want to do a flux integral with vector calculus, you can type flux and then vector field. Well, that's your curl. And then the Cartesian coordinates, and then give your surface, which is this hemisphere with the radius 2. And you're, in problem 6, you're only doing part of it. You see, you're coming down from the North Pole to well, a colatitude of 30 degrees, so 60 degrees north latitude. So you're up around Anchorage, I guess, and well, north probably of Oslo and Stockholm, northern Russia, and so on like that. Anyway, if you have entered the field and the surface and your limits, it'll do the flux integral for you. And notice what I did after 4. I did the same thing, except that I went clear down to the equator. See, the P is the phi, the colatitude angle, and I went 0 to pi over 2, so that was minus 5, 12 pi. And then the next one I did was from pi over 6 to pi over 2, which was the minus 504. And you see the difference there is the minus 8 pi. So what I was trying to show with lines 4, 5, and 6 is that line 4 plus line 6 gives you line 5. In other words, with these flux integrals, if you are thinking of your angle down from the North Pole, you can go part way, and then you can go another part way and add them together, and that's the same as if you went all the way. So that kind of thing works. Then if you were doing this the other way, in other words, if you were actually going to work it by hand, you'd have your expression, let's see, this would be the this would be your curl F dot N. If you actually did your curl F dot N and did the dot product, and then did that as a double integral, that would be what you'd be doing if you did it by hand. And so that's 7 and 8, and you see you get the same thing. And then again, 9 and 10 would be the dot product dotted out and going 0 to 2 pi, and again, if you look at line 8 and line 12, the total is the same as the line 10. So if you look at problem 13, which we did over there under the clock, I didn't do anything except just get Maple to do it. Flux in the field, and which is our curl, and the surface, and you see the 12 pi, which is what we have there, right there. And then if we look at, let's see, we did 17 and 18, didn't we? So let's go to the back. If you look at 17, I have the field, then I do the curl, which is the minus 5 K, if you use I, J, and K, line 24. So then I do flux, that field, and then my surface, which is this hemisphere, 0 to pi over 2, and I get the minus 15 pi out of Maple, which is there. And then with problem 18, I have my field, do the curl, which is line 27, and then ask for the flux, and that's line 28, and that's this, which is 0 because those integrals are. Okay, so then let's look at, let's see. I think this is really the same, this other set of Maple, I think is really the same thing. It's, I think the one that I gave you has everything that this other one does, but I'll give you this anyway. I don't think there's anything really different. I think I did these at different times. But the one we went to includes this and has the picture. Anyway, you might as well have it. So what we'll do tomorrow then is talk about the divergence theorem, which is this part. And so typically what we would do is do flux integrals over a closed surface like a sphere, complete sphere, or a box or something by computing the divergence and then working that as a triple integral of the scalar function, which is the divergence over the interior of the box or of the sphere. So some of the problems want you to do the flux integrals, say, on the 6 sides of the box and see that the 6 of them add up to the divergence integrated through the volume. So that's where we're going. Then after vacation, the 2 days, we'll worked with the 4 Maxwell equations and the physics that all this was invented to do. And then the week after that, you can spend the 2 mornings playing games with the CWI outcome and assessment test. And that's, of course, what it is playing games, because that's what school is, in a very real sense, but certainly so is American politics.